Hello students, all are welcome to my online class. Today's class is about filling of orbitals in an atom. So we are starting now. Filling of electrons into the orbitals of different atoms takes place according to the above principle, which is based on the Pauli's exclusion principle, the control of the maximum multiplicity, and the relative energy of the orbitals. So let us discuss what is above principle. The above means build up. That means electrons should be filled in the orbitals from lower energy to higher energy gradually. When we build a building, we arrange the bricks from lower to higher. So, similarly, the electrons are filled up in the orbitals from lower energy to higher energy. The word above in German means building up. The building up of orbitals means the filling up of orbitals with electrons. The principle states in the ground state of the atoms, the orbitals are filled in order of their increasing energies. In other words, electrons first occupancy the lowest energy orbital available to them and enter into higher energy orbitals only after the lower energy orbitals are filled. The order in which the energies of the orbitals increase and hence the order in which the orbitals are filled is as follows. 1s, then 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 4s, 5d. Look at the figure. The first cell has only s orbital or s subcell. The second cell has two subcells, S and P. The third cell has similarly S, P and D subcells. Similarly for fourth cell, S, P, D and F, and cell is for fifth cell. For sixth cell, S, P, D is enough, and for seventh cell, S and P subcells. So, according to above principle, the electrons will be filled up in lower to higher energy levels. So, if we draw the straight lines from here like this, so the lowest energy is 1s, then you approach, proceed, 2s, then you will get 2p, then 3s, 3p, 4s, 3d, then 4p, then 5s, then 4d, then 5p, then 6s, then 4a, now 4 electrons, and 5d, then 6p, then 7s, then 5s, 60, then 7. All the elements can be filled up with electrons with the deep energy levels. This is the building of electrons in this energy order. So, suppose because consider the element carbon. What is the atomic number? Atomic number is 6. So we get 1s, 2s, and 2. There are 6 electrons. We fill up like this: 2, 2, 2. That means the electronic configuration of carbon is 1s2, 2s2, 2. If we notate it in box notation, we get like this: 1s, 2s. What are the other rules? Rules of maximum multiplicity and power exclusion principle. Means you have to know Ohm's rule and power exclusion principle. What is Ohm's rule of maximum multiplicity? This rule deals with the filling of electrons into the orbitals belonging to the same subcell. There is orbitals of equal energy called degenerate orbitals. It states pairing of electrons in the orbitals belonging to the same subcell. Suppose P, D or A does not take place until each orbital belonging to that subcell has got 1 electron each. That is, it is singular orbit. Since there are 3p, 5d and 7f orbitals, therefore the pairing of electrons will start in the p, d and f orbitals with the entry of 4th, 6th and 8th electron respectively. It has been observed that half-filled and fully filled degenerate set of orbitals acquire extra stability due to their symmetry. What is our power exclusion principle? The number of electrons to be filled in various orbitals is restricted by the exclusion principle given by the Austrian scientist Pauli in 1926. According to this principle, no two electrons in an atom can have the same set of 4 quantum numbers. Pauli exclusion principle can also be stated as only 2 electrons may exist in the same orbital and these electrons must have opposite spin. This means that the 2 electrons can have the same value of 3 quantum numbers n, l, ml, but must have the opposite spin quantum number, that is, ms will be different. The restriction imposed by the Pauli exclusion principle on the number of electrons in an orbital helps in calculating the capacity of electrons to be present in any subcell. For example, subcell 1s comprises of 1 orbital and thus the maximum number of electrons present in 1s subcell can be 2. In P and D subcells, the maximum number of electrons can be 6 and 10 and so on. This can be summed up as the maximum number of electrons in the cell with principal count number n is equal to 2n square. Using above principle, Pauli exclusion principle and Ohm's rule of maximum multiplicity, we can do any electronic configuration of any element. Suppose hydrogen, atomic number is 1. So electron will be filled like this. That means the electronic configuration of hydrogen is simply 1s1. If you represent in box notation will be represented as this one is. So for helium, 2 elements, 1 is 2, the box condition will be 1 is 2. So for lithium, 1 is 2, 2 is 1, 1 is and 2 is. This is the box condition of lithium. Similarly, if we valence is 4, the electronic configuration will be 1 is 2, 2 is 2. Box condition will be like this. For boron, boron is our atomic number 5, so the electronic configuration will be according to above principle, Ohm's law, and power exclusion principle. 1 is 2, 2 is 2, 2 is 1. The box condition will be 1 is 2 is. For carbon, it will be 1 is 2, 2 is 2, 2 is 2. For nitrogen, for oxygen, so the box condition will be like this. In case of neon, all the subsets are completely filled up. Similarly, for sodium 11, the electronic configuration will be according to above principle, Ohm's law, and power exclusion principle. The electronic configuration will be 1 is 2, 2 is 2, 2 is 6, 3 is 1. Similarly, for magnesium, we are writing neon 4 and atom was able to filter like this 3s2. For aluminum, 3s2, 3 and for silicon, for phosphorus, and for sulfur, and similarly for chlorine 17, in core 3s2, 3p5, and for argon, the outermost is completely free. If you try to do the electronic configuration of suppose copper, this 29, the atomic number of copper is 29. So the electrons will fill up like this: 1 is 2, 2 is 2, 2 is 6, 3 is 2, 3 is 6. What will be next? So between 4s and 3d, according to above principle, you know the energy of 4s subshell is lower than that of 3d subshell. So electron will be built up in 4s before the 3d subshell. We count the electrons: 2 plus 2, 4, 6, 10, 12, 18. Rest electron need 11 electrons. You have to put up the electrons here 2 and here 9. So the electronic configuration of third electronic configuration of copper is 1:2, 2:2, 2p6, 3:2, 3p6, 4:3, right? Not 3d10, 4:2, 4:1. Okay. Similarly for zinc, we call copper as transition element but not zinc. Why? You see the electronic configuration of copper, the ground state electronic configuration of copper is argon core 4:2, 3d9. That means 3d subshell is partially filled. So it may be called as transition element because when 2 electrons removed from copper, it will be converted to Cu2 plus ion, and even in Cu2 plus ion, the electronic configuration will be 3d9, argon core 3d9. As there is partially filled 3d subshell, it is called transition element. But in case of zinc, even in zinc 2 plus ion, the 3d subset is completely filled up. So it cannot be called as a transition element. The distribution of electrons into orbitals of an atom is called its electronic configuration. If one keeps in mind the basic rules which govern the filling of different atomic orbitals, the electronic configurations of different atoms can be written very easily. The electronic configuration of different atoms can be represented in 2 ways. For example, one is, suppose the electronic configuration is A, P, B, D, C notation, and number 2 is orbital diagram. So it will be looks like this: S, P, and this is D. P is divided into 3 orbitals, and D is divided into 5 orbitals. So electrons will fill up in box notation will be in this fashion, or SPD notation, and this is box notation. The first notation, the subset is represented by the respective letter symbol, and the number of electrons present in the subset is depicted as the superscript, like A, B, C, etc. The similar subset represented for different sets is differentiated by writing the principal quantum number before the respective subset. In the second notation, each orbital of the subset is represented by a box, and the electron is represented by an arrow, a positive spin. That means this is with positive spin, and this is with negative spin. The advantage of second notation over the first is that it represents all the 4 quantum numbers. The hydrogen atom has only 1 electron which goes in the orbital with the lowest energy, namely 1s. The electronic configuration of the hydrogen atom is 1s1, meaning that it has 1 electron in the 1s orbital. The second electron in helium, He, can also occupy the 1s orbital. Its electronic configuration is therefore 1s2. As mentioned, this is for hydrogen, this is box notation, and this is SPD notation. For helium, the electronic configuration will be 1s2, and box notation will be 1 electron with clockwise spin and another electron with anti-clockwise spin. Third electron of lithium is not allowed in the 1s orbital because of Pauli exclusion principle. It therefore takes the next available choice, namely the 2s orbital. The electron configuration required so is 1:2s1. The box equation will be 1:2s1. Two electrons are filled up in 1s and one electron is filled up in 2s. Boron, carbon, nitrogen, oxygen, fluorine, and neon. Electron configuration will be like this. One is two is two, 2p1, 1 is two is two, 2p2, 1 is two is two, 2p3, and 1 is two is two, 2p4. And the box also will be like this for boron. This one is 2s, 2p. Two electrons are here, two electrons are here, and one electron here. For carbon, similarly, two electrons are here, two electrons are here, and two electrons with other spin. Because according to Coulomb's law of maximum multiplicity, the electrons will be filled up in subshell in same spin. Because of nitrogen similarly, you get the electron configuration like this. For oxygen, what will be next? We have to put electrons like this. The fourth electron will be put up in antiparallel spin. According to Coulomb's law of maximum multiplicity and Pauli exclusion principle, the current electron configuration of oxygen is